Hello everybody, and welcome back to BioSC 140 Human Physiology. This video will be the part 3 video of S3P3. This is lecture exam 3 material. All right, so mean arterial pressure, average arterial pressure is homeostatically regulated. Blood flow is not. Your body regulates pressure, and that pressure drives flow. So flow is equal to cardiac output. Flow is equal to cardiac output. The amount of blood that your heart pumps out over a period of time is how much flow there is in your circulatory system. So if we look at this equation right here, we have pressure is equal to flow times resistance. Well, we can rewrite flow as cardiac output. We can rewrite flow as cardiac output. Resistance, we're going to substitute the R in this equation for total peripheral resistance. That's going to represent the resistance of our circulatory system, the resistance of the tubes in our circulatory system. Now remember, resistance comes from three things: viscosity, tube radius, and the length of the tubes. So total peripheral resistance is going to be all of those factors together. So we can rewrite this as pressure is equal to cardiac output times total peripheral resistance. Let's come down here. So MAP, mean arterial pressure, is equal to cardiac output times total peripheral resistance. Well, we could leave it at that, or we could break down cardiac output. Remember, cardiac output is equal to stroke volume times heart rate. So we can substitute cardiac output for stroke volume and heart rate. So we get MAP is equal to stroke volume times heart rate times total peripheral resistance. So MAP is homeostatically regulated. You have three variables that you can control. Three variables where you can affect change on MAP. If you want to affect MAP, if you want to change MAP, you change stroke volume, you change heart rate, or you change total peripheral resistance. All right, so MAP is homeostatically regulated. Mean arterial blood pressure. MAP is the average blood pressure over time. MAP decreases, remember this chart, it decreases as we move through our circulatory system because of resistance. Resistance decreases pressure. It's homeostatically regulated via changes in stroke volume, heart rate, and peripheral resistance. TPR is estimated by, I'm going to say this word wrong, Poiseuille. Remember, Poiseuille's equation is the resistance equation. This is Poiseuille's equation, Poiseuille's law, the resistance equation. All right, so we are now going to fill out this summary chart. We're going to get into how our bodies regulate MAP using heart rate, stroke volume, and total peripheral resistance. And we're going to look at the intrinsic and extrinsic controls for it. Your body has many ways of regulating MAP. So let's start off with the top left box, the intrinsic control of heart rate. We've already talked about the intrinsic control of heart rate. Do you remember any hypotheses, any guesses as to what the intrinsic control mechanisms for heart rate is? Well, The intrinsic controls of heart rate are the autorhythmic cells. The autorhythmic cells set heart rate. Now, the SA node is the fastest of these autorhythmic cells. It's the fastest, so because of overdrive suppression, it is the main, the typical heart rate setting tissue. There is a genetic component, and it can be adjusted by extrinsic mechanisms. So the SA node has dual innervation. I do want you to know the innervation has dual innervation. The SA and the AV nodes both have dual innervation. So let's look at the parasympathetic effect. So we've already talked some about how the parasympathetic system can affect heart rate. If you increase the frequency of signals from the parasympathetic heart rate, if you increase the rate of signals, the frequency of signals from the parasympathetic system, you're going to decrease heart rate and decrease conduction. So you can see on this graph right here, the gray line is the normal autorhythmicity of a heart cell. It's down here. It depolarizes by itself, muscle action potential. Depolarizes, muscle action potential. Depolarizes, muscle action potential. Stimulation from the parasympathetic nervous system delays that time. It adds some IPSPs, right? Analogous to that, to slow down the rate at which the heart beats. Acetylcholine is released by the parasympathetic nervous system, and it binds to muscarinic receptors that should be reviewed from last test, lecture exam 2. And the parasympathetic predominates heart rate. It is the most influential when heart rates are below 100 beats per minute. The sympathetic nervous system, if you increase the frequency of signals, you increase sympathetic stimulation, you will increase heart rate and increase conduction. The sympathetic nervous system will release norepinephrine onto the SA and AV nodes, and they will bind to beta-1 receptors. The sympathetic nervous system predominates, has the largest effect when heart rate is above 120 beats per minute. So you can see again here, the gray line is the normal autorhythmicity, and when there's significant sympathetic stimulation, you can see that the time between peaks, the time between the muscle action potentials is much smaller. So intrinsic, autorhythmicity, extrinsic, parasympathetic, and sympathetic nervous system. And there's also hormones that are extrinsic controls. So sympathomimetics are your neurohormones from your sympathetic nervous system. So norepinephrine and epinephrine. Norepinephrine and epinephrine, the sympathomimetics, increase heart rate. These increase heart rate. Thyroid hormone, T3 and T4 are the thyroid hormones. They increase heart rate. There are no hormones that decrease heart rate. No hormones that decrease heart rate. Another extrinsic factor that can affect heart rate is heat. Body temperature can increase heart rate. When you sit in a hot sauna, it can increase your heart rate. That's considered extrinsic control. So we have the first line of this summary chart written out. Heart rate, intrinsic control is autorhythmicity. Extrinsic control is autonomic nervous system, parasympathetic and sympathetic. Also hormones, sympathomimetics and thyroid hormone, and heat. Now, let's look at stroke volume intrinsic control. So intrinsic control for stroke volume. There's the Frank-Starling law of the heart. This is an underlined, bolded, this is a key term. You pump what you get. If there is no blood in your ventricles and it tries to beat, how big will its stroke volume be? If there's no blood, there's no stroke volume. There needs to be blood returning to your heart, blood flowing into your ventricles in order for your ventricles to pump them out. So that's what the Frank-Starling law of the heart says. It says, if no blood returns to your ventricle, no blood will be pumped out, your stroke volume will be tiny. If a lot of blood returns to your ventricles and your ventricles get stretched and are full of blood before they, systole starts, you're going to have a big stroke volume. Increased volume, increased stretch, increased strength of contraction. Decreased volume, decreased stretch, decreased strength of contraction. Preload. So preload is similar. It's the pressure on the ventricle before ejection. So when there's an increased amount of pressure in the ventricle, you'll have an increased strength of contraction. So pressure on the ventricle before ejection. Increased pressure, increased strength of contraction. That's intrinsic control for stroke volume. Extrinsic control. Extrinsic control is going to be our usual suspects when it comes to extrinsic control. The autonomic nervous system and hormones. Those are your usual suspects. So we have the parasympathetic nervous system again. Now, some sources will say that there's no parasympathetic innervation of the ventricles, only of the nodal tissue. Some sources will say there's very sparse innervation with a very small effect for parasympathetic innervation of the ventricles. What all sources agree on is that the parasympathetic has a very minimal effect on ventricular contraction, on the strength of a ventricular contraction, on stroke volume. The sympathetic nervous system, everyone agrees, does innervate the ventricles and does have a large effect on stroke volume and the strength of the ventricular contraction. So norepinephrine is released by the sympathetic nervous system. It binds to beta-1 receptors. This increases calcium concentration within the muscle cells. And if you remember, calcium concentration in the muscle cells is like the key that starts a contraction. If you have more calcium, higher calcium concentration, you'll have more cross-bridging, you'll have a stronger strength of contraction. Hormones, we see the sympathomimetics again. What are the sympathomimetics? Off quiz time. Norepinephrine and epinephrine, they are the neurohormones produced by the sympathetic nervous system. And this increases the strength of contraction. Calcium conductance, basically if you have an increased amount of calcium in your muscle cells, you'll have an increased strength of contraction. It could be due to drugs, anything that increases that calcium concentration is going to increase the strength of contraction. Right here, we're seeing calcium concentration allows for cross-bridging, allows for contraction of the muscle cell. Afterload. So afterload decreases stroke volume. Afterload decreases. So afterload is the pressure pushing back on the ventricle from the corresponding artery. It's the pressure that the ventricle or the heart has to overcome to eject blood. Now, afterload is estimated by diastolic blood pressure. So let me give you a hypothetical situation. Right here, we have the aorta pushing back on the left ventricle. It's pushing with 80 pressure. When will the semilunar valve open, allowing blood to flow out of the left ventricle. Blood will flow out of the left ventricle the moment the pressure in the ventricle is higher than the pressure in the aorta. So the moment it passes 80 pressure, the semilunar valve is going to open and blood is going to flow out. When is the semilunar valve going to close? The semilunar valve is going to close the moment that the pressure in the aorta is higher than the pressure in the left ventricle, preventing backflow. Now, think about a situation where diastolic blood pressure is 100 instead of 80. The left ventricle does not pump any blood out until it gets to 101 pressure. That's afterload. Now think of a situation where the diastolic blood pressure is 120. No blood leaves the left ventricle until it gets up to 120 pressure. That's afterload. It's the pressure pushing back on the ventricle, the pressure that the ventricle has to overcome in order to push blood out into the corresponding artery. If you increase afterload, you decrease stroke volume. Increase afterload, decrease stroke volume. Another factor is venous return. Venous return is required for cardiac output. Venous return is required for cardiac output. To be pumped out, the blood must return to the heart. You must have venous return. If there is no return, if there's no blood in the heart isn't going to pump blood. The venous system plays a role in returning blood to the heart. Venous return is increased with venoconstriction, so venous constriction, and it's increased with muscle and thoracic pump. The muscle and thoracic pump we talked about in, I believe it was part 1, where when you activate muscles, when you put pressure on veins, it can increase that pressure and push blood back towards the heart. And we can decrease venous return with venodilation. So the veins play an important role in returning blood to the heart, and that returning of blood to the heart can affect stroke volume, can affect how much blood is pumped out with each contraction. I'm going to pause this video right here, and I will see you in part 4 to finish up this lecture. As always, if you have any questions, please contact me. I'm here to help.